Okay, today we're going to learn the last session in 1C, Stokes theorems. As I said before, when we were in school, I said there's a most important chapter in this book is chapter 15. Okay, that's when we learn the foundation for engineering courses of physics. So we learned the first three very important theorems. A fundamental theorem for line integral, that is for conservative vector field and path independent. Then we learned the second important theorem, the Green theorem. And then we have divergence theorem, and then now the last theorem is Stokes theorem. So Stokes theorem actually is related to Green theorem. Stokes theorem is three-dimensional for Green theorem. From the information I read is that I told you guys that Green went to Cambridge University, so he published 100 his theorems, and one of them was donated to the library. So when Stokes was a professor there, he got the whole of the Green theorem in the library, and he was very shocked that someone can calculate the work done, the circulation along the curve by using the circulation inside the curve. Okay, this is a flat. So he started to do a three-dimensional version of it, and then which he did right. So before I introduce the Stokes theorem, because these are related, okay, because Stokes get the idea from Green, so therefore I want to redo the Green theorem to just, not redo, kind of like refresh your memory. So Green theorem is for two dimension, a flat region, flat, okay, just like a flat paper, okay, just a flat. And then Green theorem connect the line integral, okay, line integral means doing the integration over the curve with the area inside the curve, and this curve have the simple log twist. Okay, just like curve without twisting. It means the initial point and end point meet at the same point. And Green theorem was able to bypass RT. See, remember when we're doing 15.2, we had to use RT, but Green theorem doesn't have to use RT. I put RT here to let you remind you in 15.2 we used RT. So because it's a closed curve, okay, it's a closed curve here, so Green used a ds. This ds is arc length, okay. This is arc length. So this is ds right here. And this is arc length here, okay, this is arc length. And in 15.2, they use a dr. That's because they're using this one. That's why they use a dr, but it's the same thing, okay, it's the same idea. And then so Green said as long as you have a counterclockwise, okay, counterclockwise, he used a counterclockwise as the orientation for positivity, means a counterclockwise. And use a right hand rule of thumb like this, okay, like this. The thumb represent the force, okay, the normal force, and then the finger, the forefinger, my finger, is represent the circulation. Okay, the counterclockwise. So when you're doing your right hand rule of thumb, okay, make sure this indeed represent the circulation, okay, the direction of circulation, and this indeed represent the normal force. So in this case, the normal force is a K, okay. So Green said that if you take the code, now this is circulation, inside is a code, okay. The code that's K, okay, code that's K. We learned that in divergence theorem also, surface integral. If f that's n, okay, it gives you three choices, right? Either they greater than 0, equal to 0, less than 0. Well, Green actually used the idea first. Green said these two dots together, okay, it should give you the circulation along the curve, okay, the circulation along the curve. So when you add them all these together, okay, all together is indeed the circulation along the curve, okay? So that's what Green believed. So he said that not conservative, this is same as that, okay? So he was able to get this is equal to this, okay? And this means not conservative for 2 dimensions. So times by dA, okay? So when you have a R, you need to have a dA, that's a match, okay? So you use a dA, 2 dimension. So K is just a normal vector, a unit normal vector, okay? It's a 0, 0, 1, because it's flat. Okay, when you're flat, then your normal vector will be right here, those are the 0, 0, 1. This is C has a smooth, closed curve. Smooth means that they can be piecewise smooth, okay? We did some problems can be piecewise smooth. And R is the flat region, so I mentioned that. So that's basically Green theorem. So Green theorem connect the line integral with the area enclosing the integral. That's because he believes all this is circulation, okay? All the circulation, when you add them together, is equal to circulation on outside the curve. And how do you calculate circulation here? That is equal to co dot K, okay? That's how they get that. So that's what Green did. So he published the book, and then he get to, I don't know, he donated to the library or someone donated to the Cambridge Library. Stowe was a professor at Cambridge University, and then he saw the book in the library and he was shocked. So he saw, hey, if you can do for flat, right, you can do it for 3D surface also, okay? Now, he just need to change a couple things. Look at this. He said that the line integral, he used the same notation as the Green because he's saying the surface still has to be a surface with a boundary, because this is a boundary for flat, right? But if you have a 3D surface, you still have the boundary outside the surface. So the boundary is very important because the boundary is where your circulation is. Therefore, it's the same as circulation. Therefore, on the surface, okay. So even though you have 3 dimensions, but you shouldn't change. So he said that, well, the circulation inside this is 3D surface should equal to the circulation outside. Okay, when you sum all this up, so he said all this little tiny circulation on a surface with the boundary, measure with the boundary. That means that this surface should be open in somehow. It means it cannot be like, for instance, if you have like a sphere is a closed surface, right? Because you don't know where's the boundary. In those kind of points, you have to cut them. But we are not doing any of those right now. We only do the one that with a clear boundary on the edge here, okay? So Stowe said, well, all I need to do is change my code still the same. All I need to do is my K and my N can be different, because when you have 3D, then you're not just have a flat and with a K like that, right? When you have 3D, you can be like this. That's your N, okay? And then, so this has a perpendicular. So he just changed it. He said all he needs is a change from Green. The code is still the same because every little circulation is still the same. But the K, he changed to N, okay? And then the R, because it's a flat region, now he changed the surface, okay? It's a 3D surface. And then this one, dA, he changed to ds, okay? This means the surface area. A vector that's a vector, okay? A vector that's a vector, so it becomes a scalar. So, and then now if you're going to project to from here, you're going to project down, you just see a circle, right? When you look down like this, okay, you look down from the top, all you see is just a circle. It doesn't matter how this part go up, all you see is just a boundary. So the boundary, you change the region, okay? When you change the region, your R be right here. just the flat part, okay, down here. So just R. When you project on X, Y, and then you can use a gradient to do the problem. If you project this on X and Y, okay, then your gradient will represent the N, and your dA is represent the area of the R, okay? So that is convert to here. But you can only use this one, use a gradient. You only use a gradient when the vector field is not that complicated. And then when you have the surface of function, you dot them together, happen to be easy to integrate. Normally, this is the way to go, okay? Normally, this is the way to go. This only happen if you you can integrate. Remember yesterday we did the quiz, you can do both ways, but most of the time you can only do one way, okay? This way is usually harder. This one has been, it happened to be, everything works out perfectly. So here's what Stokes believed, okay? He said, Stokes believed that even though this surface is not flat like green states, okay? He said he believed that the surface integral for coal, the surface integral, like this is surface integral, right? This we learned in 15.6 also. And in 15.7, we also learned surface integral. So this is a surface integral, okay? The surface integral for coal, the surface integral for the coal here, over a surface, okay? Over this surface here, and this is surface right here, okay? This is surface. It's equal to the circulation of the F, circulation of the vector field, okay? Around the boundary, this is boundary of the surface, okay? So that means Stokes' theorem, boundary is very important. As long as you have same boundary, same vector field, same orientation, then it doesn't matter how your surface is, you can still use the Stokes theorem. Okay, I will show you the benefit of Stokes theorem. The fourth theorem are very important, but Stokes theorem makes things a little bit more easier after that. Of course, I think he's the last person to look at green theorems. So to get the idea from green, but green is the one who laid the foundation first, okay, and then later on someone start using it for divergence theorem, Stokes theorem, and they do it better and better each time. So, but of course, it's not like which theorems are better, but I just said that they all have that do it on their own way, but they extend it to be more, I should say. They extend it to be more each theorems. So, he said, so Green said that surface integral of a coal F over a surface, okay, this one, is equal to the F, this one, around the boundary, okay, of the surface, even if the surface is not flat, okay, that's what he believed. So Green said flat, okay, Green said flat, okay, but Green died very young, okay, so he probably not able, if he wait for a few more years, he may be able to do this one also. But Stokes said 3D will be the same. And then Green's, the most important, Stokes said that if my surface is this way, or this little flat, or it will be like this, it doesn't matter. What matters is the boundary. As long as my boundary is the same, it doesn't matter how my surface is going to look like. I will still get the same result. As long as my orientation is not changing, means it's still counterclockwise, and my vector field is not changed, okay? Then you should be the same. So that is very helpful. That laid the foundation for later on I'm going to teach. So this still may have to go two parts because of I want you guys to do well in the final and then to understand, because Stokes theorem, okay, I have a student went to UCLA. He told me the first day in his engineering course, I think it was an electrical engineer. He told me the teacher used a Stokes theorem, gradient, and a few other things. He said first day in the class he only like doing 1C in one class. He says very overwhelming, but he looked at the note and he was able to understand, able to do the homework. So it's just the first semester usually tough, or first quarter when you transfer, but after a while, it's sinking in, okay, what you learn sinking. That's why learning is so important, okay. Learning is very, very important, and please get serious about this material. I know this is a tough time for a lot of students, the quantity time, because you couldn't, not used to learn that way. Okay. Now the next thing I need to do before we do a example is orientation for for STOICSTEM orientation. And there's many ways to teach orientation. I feel like, okay, the way I understand it, I don't know if it's easy for me. I hope it's easy for you guys. I use a right hand, the green STOICSTEM, you have to use a right hand rule of thumb. Okay, right hand rule of thumb. So because he does 3D, so I'm going to draw 3D pictures. So this is a positive Z. Okay, so this is a 3D surface. I just need to make sure I positive Z. And then he has a little bit circulation inside. Okay, so what he believes the circulation inside is sum them out is equal circulation out. Circulation inside, circulation over the surface equals circulation around the boundary. So the boundary is right here. Here's my boundaries. I use a orange color. This is actually inside the, this is on the other side. Okay, you couldn't see it. So STOIC has to be a right hand, positively counts as a counterclockwise. So if he didn't mention it, you're going to assume it's a counterclockwise, okay? So he says that you use the right hand rule, your finger, just like I did earlier. The finger represents the circulation. Your thumb is represent the Z component on your end, okay? So your end is, I'm going to use the green. The end has a perpendicular to the surface. Okay, that's my end. And then, so as long as you follow this way, as long as you can follow your right hand, this represents your end, your thumb represents your end, and then this is the end here also. And then your forefinger represents your circulation. And your comes out your end is to give you a positive, represent the last number, represent the Z component should be positive. Okay. Now if you're gonna fit this one, you rotate this picture to 180 degrees, so you'll be like this way. Now you rotate 180 degrees, be like this. Okay, upside down the bowl, and then your Z will come to here now. Okay, and then your boundary will be right here. Okay, you can completely see the whole boundary. Okay, and then your normal vector will be like this. Okay, so now let's see, if I use my right hand rule of thumb, okay, it means that this should be going up, right? This end should be going upward because of my thumb, but this is going downward. Then what happened? Then your end should look like this. So whatever you have here, and it should be a negative number for the last one. That will match. If a positive here, then you need to multiply negative in front for it to make it to be negative. Okay, so this is the format for the end. Now that's very important for STOICSTEM. Okay, surface integral is all important for the same, but STOICSTEM related to the surface integral. That's why orientation is very important for STOICSTEM. Same as surface integral. Okay, so this is very important. And if you forget, so let's say if you didn't put a negative sign here, what happened was that your answer would be the opposite of what it's supposed to be. Okay, and then you just need to fix that if that happens. Okay, so now that's the orientation. Now we're going to, the next thing we're going to do is to do a couple examples. The first thing we should, of course, we should do is to verify. Okay, we have to verify first. Because the green claimed that, but let's see if it's true or not. Okay, so we're going to verify a Stowe theorem. Okay. Oh. Okay, so we're going to verify Stowe theorem. The first one, okay, I want to do is a class example number 1. The reason is the book we have, their examples a little bit too simple, okay? And as far as I remember, okay, I was a tutor when I was in college, and I have a lot of engineering students. Their homework was not that simple at all. So when I look at these books example, I decided to pick some my own, okay? So the first problem is that we're going to verify Stowe theorems. I mean, so maybe it's a time to change the book also. This book I didn't pick it. It was picked by other professor who taught this class first. Because we opened this class in 2004, I think. And then so she picked the book. But we had been talking about to change the book. But, you know, since we have a few more professors teach this class, so everybody use a different book, so don't know. Okay, so here's a vector field. Okay, here's vector field function. And they said the surface of G is equal to x squared plus y squared. And G is less than or equal to 1. Okay, so let's graph this one first. So what's this? It's the parabola, it's a bowl, right? Okay, it's supposed to keep going, okay? So we need to cap it, okay? We cap it as G less than or equal to 1, means we cap it right here. So this is G equal to 1. So we put a plane, okay? Cover it up at G is equal to 1, okay? SY plane, okay? We said, let's carry on the top here. So we only take this apart. So this is my 0. And they said they tell the orientation is a counterclockwise. So they tell you as the orientation. So let's draw the orientation. Okay, counterclockwise. This is my boundary. Okay, the boundary, because Stowe's theorem boundaries are very important. The surface, what is surface? It doesn't matter in a way, because as long as you have the same boundary, I don't care what the bottom looks like, you get the same answer. So that's my C. That means the right hand rule of thumb, that means my K component should be positive. Okay, so now they want to verify. Okay, to verify means that okay, it's equal to okay, and now this time this is a surface area. Okay, so now we're going to start from right hand side first, left side. So I'm going to start for left side first. Okay, so start this side first. To start from left hand side, that means I need to parametric the curve. Okay, I need to find RT first. Find RT means parametric the curve. Well, look at this. The curve is now the right hand side, so you put it right here. The curve is this: x squared plus y squared equal to 1. Okay, that's my C. So my C is for the circle. Okay, so parametric circle will be X. Now some students didn't know where should I. This is when you parametric something, the first one you present X, second one you present Y, third one you present Z. Okay, some students didn't say, hey, where can I find my X? Where can I find my Y? Like yesterday in the problem. And then I feel bad because if this is in class, it's so great. The student can immediately answer me, Johnson, where do I find? Then I can immediately say it. But here, sometimes I don't get it. I don't get to see your confusion until I see your exam. Okay. So please come to my office hour. Then you can clear out anything you need. Okay. Or just send me an email, and then I will make a video on it. So your X is equal to R cosine T, right? R cosine T, and then R sine T, and then G. Now, here is I put a G here first, okay? Then I fill it in later on. And normally, well, for green theorem, okay, or green theorem, we don't do that. We don't use the parametric. For 15.2, we parametric. So by R is equal to 1 here, so it's just a cosine T and sine T. My G, well, my G is not on the XY plane, okay, it's on the top. So my G is equal to 1 here. Now watch it. Your G is not equal to 0 here because you're not in the bottom here, okay? In the right here. So you're right here in the position for G equal to 1. Okay, that's where it goes. Now we're going to take R prime T equal negative sine T, cosine T, and then 0. Now we're going to take the vector, or we have to put this inside the vector field also, okay? You know the book that we have, the vector fields are always very simple. No, the truth is the vector field is not always that simple. So we have FT, so we have to put this, replace the YG and all this stuff. So my FT, so I'm going to, okay, here they go, FT first. So my FT is equal to, you know, I actually keep it first and then change it later on. Well, here's what I do, okay? Before I change it, I put the 1 inside here so that I don't have to, I simplify first actually, but it's okay, we don't have to do that. And then my Y is equal to sine T. And then my G squared is equal to 1. So these are all 1 here, like that. So my sine T plus 6 cosine T. Okay. And then X G squared, so G again is equal to 1. Okay. So I don't need to care about it. So cosine T. And then plus a 2x plus a 2 cosine T, so become 3. Okay. And then 2xy, this is a 1. 2 times x times y, so 2 times x, that's a 2 times the cosine times the sine is a sine 2t. Okay. Now I'm going to take this one, that's the R prime T, so I'm going to erase this part. Okay, I erase it so I have more room. Okay, I don't need it anymore because I already did that part. Or you know what, I do need it later on, so I'm going to erase this part. I wish I have a bigger board. Next time I might teach in a software, so that way for my math too. Okay, so now I take F dots R prime T. Okay, that equal to this dot this, so it's equal to negative sine square T, okay, plus 6 cosine T. And then this dot this is a plus 3 cosine square T. Oh, yeah, and then this is 0. So, and then I'm going to simplify this one. Okay, I made this one to be 1 minus a sine square T. yeah, this, let me see. This starts like that. This starts by this. And do I missing something? Minus. Oh, I forgot to dot this one, huh? This is a negative sine square. And then I forgot that the second one. I forgot the sign. I said A, doesn't seem right. Okay. And then I simplify this one. I made this to be 1 minus a cosine square. So after I simplify, it becomes like this, negative 1 plus 4 cosine square t plus, and then I made, this is a minus here because this is a minus, okay? So this is a minus here. And then minus, this I make it to be 3 sine 2t. It's just an easier integrate for me later on. Now I'm going to integrate this part. The circles go all the way around it, okay? So therefore 0 to 2 pi. And then negative 1 plus a 4 cosine square t minus 3 sine 2t. And then dt. And I taught you guys, I said that if they carry up power, okay, and then the sine cosine just equal to 0. So I told you guys last time. So therefore you can see that this is just equal to 0. I don't need to worry about that. And then this one comes out equal to negative t. This you can make it to be 1 minus 1 plus cosine 2t over 2. Okay, and then it comes out is when I integrate, it comes out t. Some say maybe still integration. Okay, it's the algebra. You forget to multiply or you multiply the wrong part. So I take the 2 and the 4 reduce become 2. I take out first, and then integrate the 1s become t. This one become plus 1/2 of sine 2t. Okay, and then 0 to 2 pi. Again, this up power, that is also go to 0. So it become t. This is negative t plus 2t is a t, 2 pi. So the answer equals 2 pi. So that is for one side. Now I need to go the other side. Okay, so I first calculate the work done along here. Okay, because those said the work done along the boundary of the surface is the same as the work done on this circulation. Okay, circulation is same as work done. Circulation around the boundary, okay, is same as circulation inside on the surface. Okay, on the surface. So this is surface here. This orbital circulation. So now we did the one on the boundary. Now I'm going to do the one on this little circulation. Okay, since they also get 2 pi. So I get the left side of it. So the answer is equal to 2 pi. So let's remember that. Okay, so that way, so this one is a 2 pi. The work done is a 2 pi. Now I'm going to see the work done on here. Would that also equal 2 pi? If a yes, that means it's still is right. So I'm going to do the right hand side. Okay. So Stowe believe that ds, this is same as, let's write one more steps, is equal to okay, so I did this side already. Okay, it means I did this side. Now I need to do this side. So let's see what that side is saying. So I need to find co first. Okay, co is equal to I j k. Okay, del x, del y, del z. And then I put this there. So that'd be yz squared plus 6sz, sz square plus 2x, and then 2xyz. So I'm not gonna, you guys all do very good on the determinant. And a lot of students take it very serious. I can see in this quiz and studying very hard for it. Majority of students improve their quiz score. So when I actually get my code, and then it equal to 0, 6x, and then 2. That's what I get. Now we have to, because I erased the surface of function is they didn't give us, it was x squared plus y squared equal to 1, right? So the g they gave us is equal to x squared plus y squared. This one's on the top here, but the surface of function represent the bowl, the side of the bowl, okay? It's represented by this one. So this one I can just parametric the bowl, okay? So I can use r, x, y. I don't have to use other because to parametric the bowl is easier just to use x and y. But sometimes it's also can be done by using u and v like that also. So it just really, they're the same, okay? Usually for the bowl upside down or flip down like that, those kind of situation I tend to just keep the x and y. So that way, because it's easier for me, x, y, because this is no square rule, nothing, so easier to take the derivative. So this is x squared plus y squared. Oh. And then now I'm going to go Rx. Because I need to find n now. Once I find the code, I need to find n. Okay, where's my n? My n is right here. Okay. Okay, I need to find the n. Where's my code? Oh, my code's inside here. Inside this part. Code's inside the circulation, okay? So I need to go code.n. I need to find my codes. That's the function represent, that's the vector function represent the code here. And then now I need to find Rs. Rs equal to 1, 0, 2x, okay? And then what about Ry? Ry is equal to 0, 1, 2y. And then I need to find Rs dot, I need to find the cross because this one, the n, there's no surface function, so you have to use a cross product because cross product gives us a vector. We couldn't find a gradient, so cross product gives us a vector perpendicular to the surface, right? Okay, so when I cross them, okay, then you go I, J, K, 1, 0, 2x, 0, 1, 2y. And to save time, here's what I get. I get negative 2x, negative 2y, and then 1. Okay, the most important is the orientation now. Because the 1 is a positive here, the 1 is a positive. I mentioned earlier, if you use a right-hand rule of thumb, that means that your last, the G component, the K component, okay, the K, it should be positive number, which is a match, okay? So therefore, your orientation is perfect. You didn't make any mistake. If you are negative here, then you need to multiply negative in front. That means you make a mistake on the orientation. So now, after we get that, then we're going to put inside the formula. So we have the code here, okay? So I make sure I don't erase my. And then not a student they're able to do that, but then after that, it's tough for them to see what is the formula they're going to, what's the limit. I can see there's a second thing that students have mistake on. Okay, now when you use, remember I mentioned it yesterday in the video for the quiz, if you use the x and y here for your parametric the function surface, you must use a ds dy, okay? So I'm going to put right here. So that means that you're going to use a dx dy or dy dx, okay? So then you follow here. So your right hand side is the surface integral. That's n ds will equal to, now don't put the limit yet, okay? And then dot them first. When I dot these and that together, to save time, I tell you what I get. When I dot them, it's equal to negative 12x plus 2. Negative 12xy plus 2. And then these are the dy dx or ds dy, okay? So it doesn't matter. And then don't put the limit yet. Why? Because I'm going to show it to you, okay? Because if you're going to look at the bowl from the top view, and then what you see, the bowl is just become a circle. Okay? Your ds dy is on the xy plane, right? So this is x and this is y. It's a circle. Therefore, you can convert to use a Jacobian to use a dr d theta. Okay, then you put the boundary. Otherwise, you're going to have a x from here to here, but y be a circle. Then we log to integrate, right? That would be, do not do that. Okay, I think that one still made a mistake. You're going to be put yourself in a really ugly situation. Okay. You cannot say, oh, let me integrate this a circle, right? Or let me go negative 1 to 1, this. This is a work done circulation. You couldn't cut them either. You couldn't say, oh, 0 to here. No, this is a work done. Work done, because the circulation on the here, on here, the work done is different. So you couldn't, like, oh, let's cut it to 4 parts. So instead that, you just convert everything to dr d theta using Jacobian. So that means your theta be 0 to 2 pi because you're going all the way of the circle, okay? And then your r's from 0 to 1 because that's x squared plus y squared equal 1. And then convert your x using your when we parameter the function, okay, ds dy, in the very beginning when we parameter the function, and that you follow the same thing because it's a polar, kind of like a polar coordinate, right? So your x equal to r cosine theta, y equal to r sine theta. So this is negative 12 r cosine theta, and then r sine theta. So you're gonna have a square, okay? Okay, and then because every x and y convert to in terms of r and theta, so plus 2, and then r dr d theta. And then I mentioned earlier, I said that if you're going to have a odd power here, it's going to be 0, right, for 2 pi. So if you want to do 2 pi first, okay, you can do theta first. This is going to be 0, and this just what? So this is going to be 0 here. So this whole thing going to be 0. Okay. And then this is gone. Okay. And then you need to give a theta here. Okay. Give a theta here. So the theta will be 2 pi. That's from this one. Okay. And there's a 2r here. And that's equal to 2 pi. And then now that will integrate this as r squared. And then also equal to 2 pi. So you match the answer on your right, on this side, okay, on your left side. So that means that this indeed equal that. So that implies that r prime t dt in this equal to okay. So we verify green theorems, verify Stokes theorem. So they do equal to 2 pi. So that means the circulation on the boundary, it does equal to sum of circulation on the surface, okay, on the surface. So that tells you the important part of the Stokes theorem is that I don't care what this is. As long as I can calculate the boundary of the circulation, that means that that is equal to circulation on my surface. So that is the most important given to you, okay? Giving you the fact. The last thing, before I cut this video, I have one point to do is that, do you think that with green theorem, Stokes theorem, I'm so sorry, keep saying green theorem. With Stokes theorem, always, will you use a d psi factor for Stokes theorem or d psi factor for Stokes theorem? So, because Stokes theorem connect them together, so he said this is equal to that, right? Do you think if you use the left-hand side, easier to do, or use the right-hand side, easier to do? The problem, we just show it to you, both sides are almost the same, but sometimes the one side clears better than the other side. So here's one example I can find from the book that can really tell us. Then I will cut the video. This is a part 1 video, okay? Then I will cut the second video. I'm going to show you all the benefit of using Stokes theorem. That one boundary, different surfaces. Okay, will they get the same answer? So number 10, here's a homework problem number 10 from the book. They say use a Stokes theorem. Okay, use Stokes theorem to find the work done. To use a Stokes theorem to do these problems. Okay, they say f equal to 4xg and then y and then 4xy. And then the surface is g equal 9 subtract x squared subtract y squared. G is greater than or equal to 0. So they say use a Stokes theorem. That means Stokes theorem is, okay, or you can use a ds, or you can use r prime dr. So it's either one or three is okay. Sometimes I don't want to write so much. I just use a dr, or you can use a ds. Okay. So if you use a ds, that's fine also. If you use r prime t dt, that's okay also. Okay, it's equal to this. Okay, now when the surface vector field is not that complicated, these sides are easier to do. Okay, this is a good to do when the surface when the vector surface function is very complicated. Not surface function, I'm sorry, when the vector field function is very complicated, because the code can write out some of the term for you. Okay, so, and then these ones are harder to, this one just take the f, but this one take the code of f, so take out some of the partial derivative. So it's nice to do it like that way if this is complicated. But this is a very simple vector field. I will always try this side first, okay, if they're very simple. So they gave a surface like this, so that means it's not that high either. So let's grab this one. This is an upside down bowl. They kept it on the xy plane. Okay, they say only take the xy plane up. So this is a 9 here. And then now we're gonna, if I use this side to parametric the RT, I need to find RT for my boundary. So my RT, so this is C here. They didn't tell us the orientation, so we assume it's a counterclockwise. Okay, so right hand rule of thumb. So RT, well, when you're not using this side, you don't need to worry about the end, so then you don't have the problem about the negativity, those things. So this will be X, Y, Z, and your x equal to 3 cosine t, okay, because x squared for the boundaries, x squared plus y squared equal to 9. So the something forget to take the square root of that. Make sure you take the square root of this, okay? Don't put the 9 here, it's a 3. And I can see that mistakes come from small mistake, like algebra mistake, and it's not worth it, okay? Now this time your t is on the xy plane, so that's equal to 0. And then r prime t equal to negative 3 sine t, 3 cosine t, and then 0. And then ft is equal to, now, replace it. Say x equal that, y equal that, z equal that, okay? So your 12, that's nice. Z is equal to 0, so my first term is 0. This is good. My y is just equal to 3 sine t. And my 4xy equal to 4 times 36 sine t cosine t. And I'm going to dot them together. F that's r prime t 0. This is 0 also. This is equal to 9 sine t cosine t. And I make it to be 9 over 2 sine 2t. Just easier for me to integrate. And then from 0 to 2 pi, but guess what? 9 over 2 sine 2t. All power equals 0. Okay? So these sides are way faster than that. You can try it at home to see if you're going to get 0 also on this side. So I bet you take it longer because I tried it. Okay? It takes me a little bit longer to do the problems. So that's for the part 1 of a Stokes theorem. The part 2 of Stokes theorem, I'm going to show you the benefit of changing the surface. As long as my boundary is not changing, I will still get the same solution.